Welcome to Corrosion Clues, the podcast where we prove that chemistry isn't just confined to lab bench. It's a powerful tool used to solve massive real-world mysteries. I'm your co-host, Vanessa.
And I'm Yi Fann. Today, we're driving into a forensic investigations of a major structural disaster in Malaysia, the 2009 Sultan Mizan Zainal Abidin Stadium roof collapse in Terengganu.
Imagine a massive state-of-the-art stadium roof collapsing just 1 year after completion. Structural engineers pointed fingers at design flaws, welding issues, and shifting joints. But as analytical chemists, we look closer at the atomic level.
Exactly. Because the stadium is situated in a coastal environment, a lingering question remained. Was it purely bad structural design, or did the coastal air itself play a silent, destructive role?
To crack this case, investigators collected rust and material scrapping from the failed steel-based frame joint and bolts. They brought them to the lab and searched for the chemical smoking guns, specifically chloride ions from marine salinity that cause aggressive pitting corrosion.
Today, we have a panel of 3 forensic chemists to break down how wet chemistry exposed the truth. Welcome, everyone.
Thank you for having us. To identify if chloride is the culprit, the primary wet chemistry technique that deployed was Argentometric titration, specifically for more method. This is a precipitation titration method that relies on a very straightforward and also a beautiful chemical reaction.
I see. Can you walk us through the science of the device? How does it work?
So we are going to take our extracted chloride sample and titrate it against a standard solution of silver nitrate, which is AgNO3. The silver ions Ag plus instantly react with the chloride ion Cl minus in the sample to form a white and insoluble precipitate of silver chloride, which is AgCl. To know when a reaction is finished, we use a potassium chromate indicator. The moment all the chloride ions are completely consumed, the very next drop of excess silver ions react with the chromate indicator, which form a distinct reddish-brown precipitate of silver chromate. That intense color change made our exact endpoint for this experiment.
Fascinating. It's completely visual chemical indicator, but was there an alternative method considered to confirm these results?
Yes, forensic labs often cross-reference volumetric titration with a classic weight-based approach, which is precipitation gravimetric analysis. Instead of measuring the volume of a liquid reactant to hit an endpoint, we add an absolute excess of silver nitrate directly into the solution. This forces every single chloride ion to precipitate out as solid silver chloride, which is AgCl. Then we are going to filter out the solid and wash away all the impurities and dry it completely in an oven. Then finally, we weigh the mass on an analytical balance to stoichiometrically calculate our chloride level.
2 different chemical paths to find the same chloride ion, Professor Ning. As our critical evaluator, how do these 2 methods stack up against each other for real-world disaster investigations?
Well, I think it's a classic battle of split and simplicity versus absolute precision. Gravimetric analysis is widely considered as a gold standard because it doesn't require standardizing a titrant, and it also has incredibly high accuracy. However, its massive drawback is that it's incredibly tedious. You have to coagulate the precipitate, filter it, wash it, and then dry it to a constant weight, and then let it cool down. This process can take about a few hours per sample.
I see. And time is something investigators don't have when public safety is on the line.
It is exactly as you said. So we now look at the Moore method. It is remarkably faster because the titration in the Moore method just takes a few minutes. The apparatus is highly portable. You can literally set up a burette and stand right at the field investigation site in Terengganu. It is also highly cost-effective and perfectly optimized for macro concentration of ions, which is exactly what you find in heavy structural rust.
Are there any limitations to the Moore methods that the team had to watch out for, Professor Ning?
Absolutely. The solution must be maintained strictly between a pH of 6.5 and 9.0. If it's too acidic, the chromate indicator turns into dichromate and you won't be able to see the endpoint color change. On the other hand, if it's too basic, silver hydroxide precipitates out, which ruins your data. However, overall, given the high volume of the boat and structural samples that you probably need to screen, the Moore method is definitely justified as a superior operational choice for this scenario.
Before we can run these titrations, we can't just throw a rusty structural boat into a beaker of water. Dr. Weiss, walk us through the crucial steps of sample preparation. How do we turn a solid piece of debris into something that we can analyze and become an analytical data?
Right, so let me explain about this. The sample preparation is where analytical chemistry succeed or fail. First, we have to perform extraction and crushing. The rust and the surface corrosion scales are carefully scraped off. The failed steel space frame joints and crushed into a uniform powder using a mortar and pestle to maximize the surface area. Second is about the digestion. We have to dissolve a precisely weight amount of this powder into the distilled water. If the oxides are stubborn, we use a mild non-interfering acid digestion to fully liberate and trap chloride ion into the aqueous solution. Then thirdly is about the filtration. So the structural scrapings contain insoluble carbon steel fragments and grease. So we have to pass the mixture through the quantitative filter papers to obtain a perfectly clear and transparent filtrate. If the solution is cloudy, it will mask our reddish brown endpoint color change. And finally, I'm going to explain about the pH adjustment. So we have to test the solution and add dilute sodium bicarbonate until the pH value sits safely around 7.0 to 8.0. Only then is our sample is ready for the burette for further investigation. Yeah.
Now, for the moment of truth, let's look at the hard data. Dr. Amina, walk us through the quantitative breakdowns of the forensic evidence.
Let's look at a representative sample analyzed from one of the collapsed roof joints bolts. We started with an exact sample mass of 0.8 grams of prepared corrosion scrapings. Then we titrated it using a standardized 0.1 m silver nitrate solution. Then the burette readings show that it required exactly 22.5 milliliter of silver nitrate to hit that distinct persistent reddish brown chromate the endpoint. First, we calculate the moles of silver nitrate delivered. So the equation will be moles of silver nitrate equals to molarity times volume equals to 0.1 mole times 0.02250. Because the stoichiometric reaction ratio between Ag plus and Cl minus is strictly 1:1, the moles of chloride ions present in our sample must also equal 0.00225 moles. Next, we convert those moles into an actual mass using the molar mass of chlorine, which is 35.45 gram per mole. The equation would be mass of chloride 0.00225 mole times 35.45 gram per mole equals to 0.07976 grams. Then, finally, we determine the weight percentage of chloride in our original structural scrapings. So, the percentage we will be having after the calculation is 9.97%.
Wow, nearly 10%. Dr. Amina, interpret this number for us. How does a value of 9.97% chloride mean in forensic engineering?
Now, in the world of structural engineering, this is an absolute smoking gun. Normal atmospheric corrosion of steel yields negligible chloride percentages. A chloride content of nearly 10% inside the rust matrix proves that marine salt spray from the Terengganu coast continuously penetrated the joints. This induced severe pitting and distracts corrosion cracking, radically accelerating the structural degradation of the space frame before it ultimately snapped.
Incredible. So, while the physical collapse was a structural failure, the root catalyst was an unmonitored chemical assault by the environment.
Well, precisely. It proves that engineers and chemists must work hand in hand when designing infrastructure in tropical coastal nations like Malaysia.
That is all the time we have for today's episode of Corrosion Clues. A huge thank you to our brilliant panels of experts and to our viewers. Remember, when structures falls, look to the chemistry for the answers.
Case closed. We'll see you in the next episode. Bye bye.